So we figured out the first derivative test, which tells you, depending on how the derivative of a function changes sign from positive to negative or negative to positive, it tells us whether our x value where the derivative is changing sign, whether it's a local minimum, a local maximum, or neither. So let's look at a couple examples of this to see how it works. So let's find all critical numbers for this function, cosine squared x minus 2 sine x, and classify each one of these critical numbers as a local minimum, a local maximum, or neither. Now, one thing to notice about this function is it's periodic with period 2 pi, so we only really need to figure things out on the interval from 0 to 2 pi, because outside of that interval, it's just going to start repeating itself. So first we need to find some critical numbers. So let's take the derivative of this function. It's going to be 2 cosine x times derivative of cosine x, which is negative sine x, minus 2 times derivative of sine x is cosine x. Okay, now to find critical numbers, we need to set this equal to 0 and solve. So let's factor, why don't we factor out 2 cosine x, and then the stuff that, actually let's factor out a minus sign as well, and then the stuff that's left over is sine x plus 1. Okay, now for this to be equal to 0, one of these individual pieces has to be equal to 0, so either cosine x is equal to 0, or sine x plus 1 is equal to 0. When is cosine equal to 0? Well, this is whenever x is, let's see, pi over 2, so think about your unit circle, right? If we want the x coordinate on a unit circle to be, or the horizontal coordinate on a unit circle to be 0, where do we have to be? We have to be at the top of the circle or the bottom of the circle. So that's pi over 2. And then we can add any multiple of pi, and we'll end up with a horizontal coordinate of 0. So plus any multiple of pi, and I'll write that like this, pi times k, and k is any integer. Okay, and where is sine of x plus 1 equal to 0? Well, this is when sine of x is equal to minus 1, and this is when x is minus pi over 2, because right, sine of x is minus 1, that's the bottom of the unit circle. But we could go around the circle any number of times, so plus 2 pi k. And again, k is any integer. But actually, all of these possible solutions coming from the sine part are redundant. They're already in this list of critical numbers coming from the cosine part. So we don't need to list them again, right? We already have those numbers in our list. Okay, so remember that we really only need to, so we have our critical numbers. To use the first derivative test to figure out which critical numbers are local mins and local maxes, we need to know where the derivative is positive and where it's negative, so that we can tell where it's changing sign from positive to negative and where it's changing from negative to positive. To do that, we can actually just make a sign chart, just like we were doing when we were figuring out where a function was increasing and decreasing. So let's make that sign chart. And remember, we only need to go from 0 to 2 pi because this function is periodic with period 2 pi, well, period no larger than 2 pi. So as long as we go from 0 to 2 pi, we'll have all of anything outside of this interval will just be repeated, a repeated version of what's inside this interval. Okay, so let's plot the critical numbers in this list that are on this interval. So there's pi over 2, which is right here. And then adding pi to that, there's 3 pi over 2, which is over here. And then if we add pi again, we're outside this interval. So there are only 2 critical numbers in this interval. So now we need to determine on each one of these intervals is the derivative positive or negative. So right, we have these 3 intervals here. So let's And the derivative is right here, so let me actually write this out. So this is minus 2 cosine x sine x minus 2 cosine x. Okay. So on this interval, let's plug in 0. If we plug 0 into this, then this first part turns into 0, and the second part becomes plus 1. So minus 2 times plus 1 is minus 2. So here the derivative is negative. All right, for this middle portion, why don't we plug in pi? That seems like an easy spot. So if we plug in pi, these cosines become 0, or no, these cosines become minus 1. So let me write this out. When x is pi, we get minus 2 times cosine of pi is minus 1, sine of pi is 0, minus 2 times cosine of pi is minus 1. So this part drops out, and we get plus 2. So the derivative is positive in here. And after 3 pi over 2, well, we could plug in 2 pi. That actually is going to give us the same result as 0 just because of the periodicity. So here it's negative again. All right. Now remember, where this function switches from where the derivatives changes from negative to positive, that's a local minimum. So here, this is a local minimum. And where the first derivative switches from positive to negative, that's a local maximum. Okay. And then outside of this interval, the pattern just repeats. So the next critical number is at 5 pi over 2. And right, that is 1 period forward from pi over 2. So this must be a local minimum. And then the next critical number after that is 7 pi over 2. And that's 1 period forward from 3 pi over 2. And so that must be a local max. You can see that what's happening here is, in this big list of critical numbers, they're alternating local mins and local maxes. For a second example, let's find all the local minimums and local maximums for this particular function. We'll do this like we did the last one. We'll just make a sign chart for this function g. So g prime of x, we'll make a sign chart for the derivative of this function. So g prime of x is 2/3 times x to the minus 1/3 plus 1. All right, now we need to know what critical numbers are for this so that we can build our sign chart. And this is our first example where there's a critical number that shows up because the derivative doesn't exist. So this derivative does not exist at x equals 0. Because this negative exponent means that we actually have a cubed this x to the 1/3 in the denominator. And when x is 0, then we'd be dividing by 0. So this is undefined at x equals 0. And so we have to include x equals 0 as one of our critical numbers. But since the derivative isn't defined there, I'm going to use an open circle instead of a filled-in dot, just so that we remember that the derivative isn't 0 here because it's undefined here. Okay, and this was at x equals 0. All right, so now let's find places where, let's find critical numbers where the derivative is equal to 0, so we can set this equal to 0 and solve for x. I guess we need to multiply both sides of this equation by x to the 1/3. On the right-hand side, of course, we just get 0. On the left-hand side, we need to distribute this x to the 1/3, and we get 2/3 plus x to the 1/3. And then move this over. 2/3. Sorry, let me move it over the other way. So x to the 1/3 equals minus 2/3. So now cube both sides. X is minus 2/3 cubed, which I think is going to be minus 2 cubed is 8, 3 cubed is 27. So minus 8 over 27. So it looks like maybe I should move all of this over to the right a bit just to make some room. So here's 0, the critical number at 0, and then here's the critical number at minus 8 over 27. And minus 8 over 27, this is a critical number where the derivative exists and is 0, so we'll use this solid dot. All right, so now we can start building our, finish building our sign chart for the derivative, g prime. We just need some test values, so maybe we could plug in 1. If we plug 1 into this derivative, we get a positive number, clearly. So here g prime is positive, and so g prime is positive. From minus 8 over 27 to 0, well, it's hard to know what a nice number to use would be. How about minus 1 over 27? So 2/3 times minus 1 over 27 to the minus 1/3 plus 1. So cubed root of, so 2/3 times cubed root of 1 over 27 is 1 over 3. So that to the negative first power, so that's 3. 3 times 2/3, sorry, negative 3. Negative 3 times 2/3 is negative 2, plus 1 is minus 1. So this whole mess is less than 1. So here the derivative is, sorry, less than 0. Less than 0. So here the derivative is negative. And then to the left, well, how about minus 1? If we plug minus 1 into this derivative, we're going to get what? 2/3, negative 2/3 plus 1, and that's positive. So here the derivative is positive. All right. Now, remember, for local maxes, we're looking for where the derivative changes from positive to negative, and that happens right here. So this is a local max. And for local minimums, we're looking for places where the derivative switches from negative to positive. And that happens right here. This is a local min. Now, it might be surprising at first that we found a local minimum, even though the derivative doesn't exist at this point. But what's happening here is the original function is defined at x equals 0, but there's something happening at x equals 0 that prevents a derivative from existing there. To see what it is, let's look at a graph. So let's pull this function up on GeoGebra. So this is, let's see, x, let's see, g of x is x squared to the 1/3 plus x. So like that. Now you can see on the graph that's what is happening here is, right, our high spot, our local maximum is in here somewhere, okay, which we're expecting, right? We're expecting a local maximum at negative 8 over 27. The local minimum is right here. Well, at this local minimum, there's this sharp point. And since there's a sharp point, that's why the derivative doesn't exist. We've seen that one of the graphical features that causes a derivative to not exist is when a graph has a sharp point. And this is certainly one of those. This graph has a local minimum that's hiding at a spot where the derivative doesn't exist. But notice that even though the derivative doesn't exist at this spot, nearby, the derivative is changing from negative to positive. So even though the derivative didn't exist at x equals 0, the first derivative test still lets us notice that x equals 0 is a local minimum for this example. This does show you that on your sign charts, you do need to include spots where the function for which you're making the chart doesn't exist, and also places where that function is 0. All right, for our next example, let's find all the local minimums and maximums for this one. So we'll take a derivative. I kind of want to avoid multiplying this out just because I think it would be messy. So let's use the product rule. So differentiating the first piece, we get 3 times x minus 2 squared times the derivative of x minus 2, but that's 1. Okay, times x plus 1 with no derivative, plus the first part with no derivative, x minus 2 cubed with no derivative, times the second part with the derivative, but the derivative of x plus 1 is 1. So there's a times 1 here that I'm not going to write down. All right, so to build a sign chart, we need to know where does this derivative not exist. Well, it's a polynomial, so it's defined everywhere. Now we need to know where is it equal to 0. Well, to know where it's equal to 0, we're going to need to factor this. So we can start by just factoring out the common factor of x minus 2 squared. And that's going to leave 3 times this piece, so 3 times x plus 1 plus, and after we've factored out 2 factors of x minus 2, there's 1 left behind, like that. Okay, and now we can simplify all this. So this is x minus 2 squared. And then in here we have, let's see, 3x. There's another x, so 4x. And then 3 minus 2 is plus 1. All right, so it looks like either x minus 2 has to be 0 or 4x plus 1 has to be 0. So x is 2 or x is minus a quarter. So on our sign chart, we can put minus a quarter and 2. And now we can start plugging in some test values. So we could plug in 0. So h prime of 0. So we have to plug our test values into this formula here, which I guess is the same as this right here. So let's actually use this one. All right, so when we plug in x equals 0, we're going to get minus 2 squared times 1. So that's going to be 4. That's positive. So in here it's positive. Over here, let's plug in 3. So h prime of 3 is, let's see, 1 squared times, let's see, 12 plus 1. So that's positive. And then finally, let's plug in, how about minus 1? So h prime of minus 1 is, let's see, minus 1 minus 2 is minus 3 squared times 4 times minus 1 is minus 4 plus 1 is minus 3. So this whole mess is going to be negative. So negative. All right. So now we can use the first derivative test. At this critical number, the derivative, so this is a sign chart for h prime. The first derivative is switching from negative to positive. That means this is a local minimum. And at this critical number, at x equals 2, the derivative isn't changing sign. It's positive, but then it's still positive. So this is not a local min or a local max. Okay. To see what that looks like on a graph, let's actually graph this function just to understand what exactly is going on here. So h of x is x minus 2 to the third power times x plus 1. All right, so we're looking at the green graph, I'm sorry, the red graph now. And at x equals minus a quarter, right, there's our local minimum that we were expecting. But at x equals 2, right, here's this critical number that isn't a local minimum or a local maximum. And you can see now why it isn't a local minimum or a local maximum. It's because as we pass through x equals 2, the function is increasing the whole time. Right? It sort of pauses temporarily just for a moment at x equals 2. It levels out just for an instant, but then it continues increasing. It does not turn around and come back down. So that's essentially what happens every time you have this sort of feature in a sign chart, where the derivative is positive and then 0 and then positive again. It's this sort of vaguely cubic looking kind of shape.